So we will discuss about the example to draw the body flat here. This is example. We have one source and there are one resistor and one inductor and one more resistor here. So this is simple, the circuit. We define this is Vs, and we define this voltage between inductor and resistor R. We define this is output signals here. So this is L and this is R and this is Rs. So actually we want to know network functions. Network function H omega is output phasor over the input phasor. So from here we can calculate very simply, because VO is voltage divisions. When you transfer the log phasor, this is Rs, this will be J omega L, this will be R. Therefore, Rs plus R plus J omega L, R plus J omega L, Vs. Therefore, H, the transfer functions, network functions, is a ratio between the output and input. VO over Vs will be Rs R J omega L R J omega L. This is a network functions. So R is R J omega L R J omega L. So the other name of network function is transfer functions. So we will represent this network function H omega is Rs plus R plus J omega L R plus J omega L. We will represent these network functions as in form of K1 plus J omega 2 omega 1 plus J omega 1 omega. So this will be represent H magnitude and phasor. So if the network function or transfer function has a form of in this manner, then we will represent this form is in this manner here. Then H can be represented by three variables. What's that? K omega 2 omega 1, K omega 1 and omega 2. So the reason that we represent the transfer function in this manner is this variable in K and omega 1 and omega 2 has their special characteristics. So when you say H is K1 plus J omega 2 omega 1 plus J omega 1 omega, we call omega 1 is actually the kind of a corner frequency we already discussed about this frequency previously. Here, this one is a kind of something in the numerator. Then we call this is the corner frequency. This is a corner frequency. In numerator. We call this is 0. And omega 2 is the same. This is omega 2. This is omega 2. It is also corner frequency. In denominator. So we call this variable, is pole. It's very important terms, zero and pole. Anyway, so in this form, this characteristic over here is that the relationship between input and output can be represented in the three variables k and omega 1 and omega 2. So we call the gain k, and we call the DC gain. For example, if the omega is go to the 0, what's the meaning of that? This is a very, very, very low frequency. And DC, right here. Then when you go to the omega 0, H omega is omega go to 0, K 1 plus J omega 2 omega 1 plus J omega 1 omega. Then equal to 0, 0 equal to the 0. Therefore, that variable will be k. Therefore, we call the k as a low frequency gain, or other name is the DC gain. So in this case, H was Rs plus R plus J omega L, R plus J omega L. When you go to the DC gain, omega go to the 0, then this go to 0, The remaining thing is Rs plus R and R. This will be the gain, the DC gain. Or We can get this again in other way. H was Rs plus R plus J omega L, R plus J omega L, and we rewrite these transfer functions in this manner. So to do that, we rewrite this equation Rs plus R and 1 plus J Rs plus R and omega L and R 1 plus J R omega L. So that will be Rs plus R and R and 1 plus J is important. Omega Rs plus R divided by L and 1 plus J omega R divided L. So this is K1 plus J omega 2 omega 1 plus J omega 1 omega. Here this is K, this is omega 2, this is omega 1. So K is Rs plus R and omega 1 is R over L. Omega 2 is Rs plus R over L. So in this case, omega 2 is larger than omega 1. And we want to get a gain. Gain means the magnitude of the net of functions. That will be K 1 plus omega 1 omega squared 1 plus omega 2 omega squared. So I will draw. Okay. Yeah, we'll do the Bode plot. So actually, hold on. We will draw. We need more space. So I think we need to move down a little bit. Here. Okay. So, I mean, here, okay, can represent the H. H is K 1 plus J omega 2 omega 1 plus J omega 1 omega, and here K is Rs plus R and R. Omega 1 is R over L. Omega 2 is Rs plus R over L. Then we want to draw the Bode plot. Actually, Bode plot has two figures. The first thing is the magnitude. The second thing is phasor of H. So H is a magnitude of H. and phase angle. So first we will draw the depth values. And body flat is two figures: magnitude of depth and phase angle. So first we want to draw the body flat in the magnitude. Okay. Magnitude is in this manner here. This is magnitude, so we need to draw the body flat. So to do that, we need to divide this body flat based on the corner frequency. We have two corner frequency, omega 1 and omega 2. So what happens when h? We need to approximate. We need to approximations. So h is when omega is very small compared omega 1, then h will be k 1 plus j, and I'm sorry, omega square 1 plus omega 1 omega square. Then here omega is very small compared to omega 1. Also omega 2 is larger than omega 1. This is very small compared to that, so it will be 0 and 0. So that will be like k. When omega is between omega 1 and omega 2, then h will be k 1 plus omega 2 omega square 1 plus omega 1 omega square. Then because omega is higher than omega 1, but omega 1 is very low, very small compared to omega 2. Therefore, this is, we can go to 0. So the main thing, and because omega is higher than omega 1, so this is larger than 1, so it can be moved here 0. So that result will be k, and this is 1, and this is omega 1 omega square. That will be k omega 1 omega. The third thing is when omega is larger than omega 2, then that will be k 1 plus omega 2 omega square 1 plus omega 1 omega square. In this case, because so this is larger than omega 2, so this is larger than 1, so we can go 0. No, this is very small. This is very small, so we can rewrite that. We can ignore 1 and 1 here. So the main thing is k, we can ignore the terms, omega 1 omega square omega 2 omega square. So it will be k omega 1 omega 2. So we can get the approximations in this manner. So here we want to represent the magnitude of h is in dB, because the body flat use the dB. So dB is 20 log 10 and h. So we insert h in that approximation here. So that will be at first 20 log 10 and this variable, and this variable, and this variable. We go here. We go insert it here. So it will be k. So when omega is small, omega 1. Or it will be 20 log 10 and that variables k omega 1 omega. You know that this is local qualifications. So you know log a and b can be represented log a plus log b, and log a over v is log a minus log b. Therefore, that can be represented 20 log k minus 20 log omega 1 plus 20 log omega. So when omega is between omega 1 and omega 2. Another thing is distance. 20 log k omega 1 and omega 2. So they can be represented 20 log k minus 20 log omega 1 plus 20 log omega 2 when omega is larger than omega 2. So we can represent the body plot in this manner here. So now we will draw the body plot in the magnitude. We are ready to draw the magnitude of the body plot. How can you body plot? How can draw the body plot here? It's quite simple, you know that. So we make some values, some axis here. This manner, and make axis this manner. Here, the axis is actually is not omega; it's a log omega. Right here, and we define this is log omega 1. Define is actually I don't know about the value of that anyway. There will be log omega 2. When use do this here. Here, actually, when in this area omega is smaller than omega 1, then it means that this region here, in this region, the figure that is the magnitude of h actually in dB. What's the meaning of that? When you represent dB, then we draw not h but log 20 log h. So when when omega is smaller than omega 1, that is a constant variable. this is a constant variables because the k is a given variables. So this figure, will be, this the graph looks like that. Maybe this variable will be 20 log k. That is that variables actually. This man here. Then second thing is here. That is between the omega 1 and omega 2. So when omega is omega 1, according to the line, when you insert the omega 1 here, we insert omega 1 here, then we insert omega 1 here, then 20 log k minus 20 log omega 1 plus 20 log omega 1 at omega is omega 1. So we eliminate the variable 20 log k. That means here is the variables. How about the omega 2? Then 20 log k minus 20 log omega 1 plus 20 log omega 2 at omega is omega 2. So the name of that is actually, I don't know a variable that name. Anyway, when here we get, because omega 2 is larger than omega 1 in these systems, so maybe that variable will be larger than that variables. So maybe here we define that variable is 20 log k minus 20 log omega 1 plus 20 log omega 2. So we have 2 points between omega 1 and omega 2, and this is about the log omega. So this is a log omega. So this is the straight line, right? And this is isolations. So the figure looks like that. Okay. This figure is this line is 20k minus 20 log omega 1 plus 20 log omega. This is a function of log omega here, and this is a constant. And third, omega is larger than omega 2s. Then this is a 20 log k minus 20 log omega 1 plus 20 log omega 2. This is constant. This is the same variable over there here. So in this case, we get that variable is in line. This is line number, this is a line number 1. This is line number 1. This is line number 2. This is line number 3. And this is line number 1. And this is line number 2. And this is line number 3. But the line number 1 is a variable, valid in omega is smaller than omega 1 here. So line 1 is valid here. And how about in this area? Omega is larger than omega 1 and smaller than omega 2 here. In this area, the line number 2 is the dominant figure. So this is dominant. Okay. And how about in this period? How about in this period? Line number 3 is dominant. So then you can draw the f variables here. So this line will be the magnitude of these figures. This is a body plot of the magnitude. I mean, actually, this is a magnitude graph of a body plot. Okay, and we need to draw one more things. Okay, we copy here, and we need to draw one more things. Here we draw the body plot magnitude, but body plot consists of two things. I mean, plot of phase angle of H. That means we need to draw the values, phase angle of that. Then also we will use the same things about the this manner. I mean, H is, we'll use the green lines. H is K1 plus J omega 2 omega and 1 plus J omega 1 omega. Then what is a phase angle of it here? And you know that the phase angle over here is, that is a phase angle. I mean, this H is a 3 component. I mean, you remember that. For example, the complex number and A, B, C. The magnitude of A, B, C is magnitude of A multiplying magnitude of B multiplying magnitude of C. The phase angle of ABC is a phase angle of A at phase angle B at phase angle C. The same manner, phase angle of B, A over B is phase angle A minus phase angle B. This is complex numbers ABC. In the same way, the phase angle of H is, we have 3 terms here. These terms, and these terms, and these terms. So this is phase angle of 8K plus and phase angle of 1 plus J omega 1 omega minus phase angle of 1 minus J omega 2 omega. So here we need to divide this phase angle of H. So phase angle of H can be divided first when omega is smaller than omega 1. Then phase angle H, there will be the phi, because this is a K plus 1 plus J omega 1 omega minus 1 minus J omega 2 omega here. We have some assumptions that omega is very small compared to omega 1. Therefore, this is very small. In the same region, this is very small. So this is this is a real numbers. This is a 0 plus, it's just 1 and minus 1. This is real number and real number. Therefore 0 plus 0 minus 0 is 0. So this is 0 degree. And second, omega is in the omega 1. Omega is on the omega 1. Then H is, phi is actually K plus 1 plus J omega 1 omega minus 1 plus J omega 2 omega here. And we insert the omega here, omega 1 at omega 1 is omega K plus 1 plus J omega 1 omega 1 minus 1 plus J omega 2 omega 1. So this is the 1. This is 1. And this is omega 1 is very small compared to omega 2. So this will be, we'll ignore this terms. So that can be K plus 1 plus J 1 minus 1. So this is 0 because these are real numbers. And this is a 1 and 1, you know, 1, 1. This is 45 degree. So this is 45 degree and minus 0. So there will be 45 degree. No, actually 45 degree. Next is omega is between omega 1 and omega 2 here. In the same manner, this is H. And then, you know, this is a very, when omega is larger than omega 1. So this is larger than 1. Therefore, we can ignore these terms here. Ignore. But omega is smaller than omega 2. So this is a 0. So we can rewrite here is K plus J omega 1 omega minus 1. So there will be, this is a real number, this is 0 degree, and this is an imaginary number, there is 90 degree, and this is a real number, this is 0 degree. Therefore, this is 90 degree. And then we have assumption that omega 2, I mean, when the omega 2 is very larger than omega 1. And 3, number 3 is, and 4 is when omega is same with omega 2. Then H to the 5 is K plus 1 plus J omega 1 omega minus 1 plus J omega 2 omega here. We insert this as omega 2 here, and omega 2 here. Then this is a 1. And this is a very large than omega 1, so we can ignore this 1. Because that is very large than 1. So we can rewrite here is K plus J omega 1 omega 2 minus 1 plus J1. So this is a real number 0, and this is imaginary number 90. This is 45 minus 45 degree, so there is 45 degree. 5 is when is omega is larger than omega 2, and H I will be k plus j1 plus j omega 1 omega. Actually, this is not j, this is phase angle, minus phase angle 1 plus j omega 2 omega. Here omega is larger than omega 2, so this is omega, this is larger than 1. Ignore, same way ignore, then k plus j omega 1 omega minus j omega 2 omega. So there will be real number 0 imaginary plus 90 degree, imaginary minus 90 degree. There will be 0 degree. So if you draw these things in the butterfly here, then we summarize here is, we need to make some point. And summarize. H phi is, at first this is a 0 when omega is smaller than omega 1, and this is 45 degree at omega is same with omega 1, and this is 90 degree at omega 1 and omega 2, and again 45 degree omega is omega 2, and again 0 degree omega is larger than omega 2. So here then we can redraw the body plot with these figures. This is a body plot of the magnitude, and we can do this. We can do this. Here. And this is a same dimensions. This is log omega, same things, but here we draw the magnitude of that here. In the second graph, we plot the page of h in dimension is degree, unit is degree. And here you know that when omega is smaller than omega 1, then that value is 0 degree. So we draw, this is it. So this is 0 degree here. Zero degree, and when here is we have 45 degree wet when omega is omega 1 here, and also between here we have a 90 degree here, and again omega 2 is 45, and again there's the 0 degree. So the figure of that is we start at 0 degree and go here and touch 90 degree and here and here. So this is phase angle of these figures. And this is a way how to draw the body plot in magnitude and phase angle here. So when you draw the phase angle, actually the tip of the phase angle if, for example, H is looks like kind of a 1 plus J omega 1 omega 1 in this manner here. So you know that when is, the magnitude of H is like that. When omega is smaller than omega 1, then what is that? That will be 1. Then when omega is higher than omega 1, then that will be, the magnitude of that is the 1 plus omega 1 omega square 1, right here. Then this is very larger than 1, so it will be looks like omega 1 omega 1. So here there will be omega 1 divided by omega. So we write here in dB 20 log H is in this area, that will be 20 log 1 is 0 dB, and in this area 20 log omega 1 is 20 log omega 1 minus 20 log omega. This is omega is smaller than omega 1, omega is larger than omega 1. So this is important, the figure of the here. And how about the phase angle? H. So when omega is very small compared to omega 1, the phase angle is 1. So this is 0 degree. And how about omega is very large to omega 1? Then this is very large, so that will be J omega 1 omega 1. So that will be minus 90 degree. How about omega is the same with omega 1? Then there will be phase angle of 1 plus J1. So this will be minus 45 degree. So when you draw the butterfly here, its important point is omega 1. So we draw the butterfly at first magnitude here, and we have two things here. This is log omega, and the same with this log omega we define. This is log omega 1. At the same point we have log omega 1 here. Here. And first we will draw things. At first is the H magnitude. The dimension is dB. How about in this area? Now that value is 0 dBs. So this is 0 dBs here when omega is smaller than omega 1. Then how about this area? Let's say, when you insert omega 1 here, there is 0 dBs. But this in this area, that this is about, based on log omega, that is minus 20. The acceleration is minus 20. So figure of that here is go down in this manner here. In this manner here. So matching of that, the one dimension is maybe about, if you say this is a log 10 omega 1, and this is log 100 omega 1, then here is minus 20 and minus 40. That is minus 20 dB per decade. So this is a magnitude of this waveform here. And how about the phase angle? So in this area, the phase angle is 0 degree. So this is a 0 degree. And at the point of that, omega 1 is minus 45. So at this point, that is minus 45. And how about when omega is larger than omega 1 here? There's a minus degree. That means minus 90 degree in this area. So we need to define the one phase angle graph. So how we can do that here? In generally, we use approximations. So log 10 omega 1, and here is log here. So we draw the line in this manner from here and this 45 in this manner here. This is a multiply line here. This is a pager. This is a phase angle of this transfer function. This is a way how to draw the Bode plot. So we have one more example to draw the Bode plot here. Example 13-3 and 1. And in this problem, we will draw the Bode plot here. Let the network function h is k j omega 1 plus j p omega in this manner. So we need to find out some special point. Where is special point? Actually, the special point is the P. This is a special point over here. So H omega can be represented when omega is smaller than P, then this K 1 plus J P omega J omega here is very small, so you can ignore that because omega is very small. This is ignore compared to the 1, so that can be represented K J omega. The same way, K 1 plus J P omega J omega, when omega is larger than P, then this is a very large, so we can ignore that terms. So the main thing is K J omega J P omega. So that will be KP. Why? Right here. Omega is smaller than P, then P omega represents 0. Therefore, H omega is K1 J omega, so KJ omega. Why? Omega is larger than P, then 1 plus J P omega, approximately J P omega. Therefore, h omega will be k j omega j p omega. That will be k p. So then what should we do at first? We need to draw the magnitude of that here. So to do that, we need to transfer the h in the division, dB. Then what we have to do is 20 log magnitude of h will be 20 log k j omega magnitude. Therefore 20 log k omega. So it will be 20 log k plus 20 log omega when omega is smaller than p. The same way, 20 log here is kp. That will be 20 log k plus 20 log p when omega is larger than p. So we need to draw the two figures, the two graphs here, this one and this one. Then what do we do here? We have one line, this is log omega. This is not omega, this is log omega. And let's say this is a point of p, therefore this is a log p. Then we draw this line will be magnitude of h dB here. So let's say at this point over here, maybe we can say this point maybe will be 20 log k plus 20 log p. So when the omega is larger than p here, then this area, then this variable is reasonable. So we can use this line here. And how about this region? How about these regions? This region we will draw in these figures. This is constant, and this is variables. This is variables, and 20 is a line. So this inclined line is 20. So what's of that? We define this is because this is a log scale. We can draw some line. This is log. This is log 1 decade of p. And this is log 2 decade of p. Then you can say because the 20, what's the meaning of that? When you decrease, if you decrease 1 decade here, then the variable is 20 is decrease. That means that, and in other words, when you go 1 decade is increased, then variable is 20 is increased. So when you say their value is 20 log k plus 20 log p minus 20, then this is a point. So line over here will be drawn in this manner. Okay. So this is the body plot of magnitude of the body plot, and line of that is 20 dB per 1 decade. And how about the phase angle? So we draw the phase angle here. Then we use it here. The phase angle H is at first when omega is smaller than P, that is an angle of kj omega. What's the meaning of that? That is 90 degree. Right? This is line. And in this kp, when omega is larger than P, so this is a constant, the real numbers, so it's 0 degree. So what happened here? So we also draw the line here. That is log omega, and we have similar lines here, and this is phase angle of H. Then we have the same point here. This is log P, and this is log P over 10. This is log P over 100. There will be log 10P. There will be log 100P. Then we can say when omega is very small to P, then the phase angle is 90 degree. Therefore, this is 90 degree. This is 90 degree. And when Kp is 0, omega is P, then that will be, when you insert the P here, then immediately K 1 plus J1 and 1. So that will be 45 degree. So here we have 45. And when omega is larger than P, that will be 0 degree. So that will be 0 degree here. An important point is this, and we assume that from the one dimension and one dimension we draw, this is a lot 10 times higher frequency. This is a dominant here. 10 times lower frequency, this is a dominant. So between here and here, we draw line in this manner here. This is a general way to draw the butterfly phase angle.